Hello and welcome to another issue of Embedded Insights newsletter. My name is Martin Schroeder at SwedishEmbedded.com, and the goal of Swedish Embedded is to help you build embedded systems faster than ever. So in this video, we're going to look at the 16 main skills that you need to develop in order to build embedded systems faster than ever. So let's get started. Many of the skills that we're going to talk about in this video are transferable skills, which means that you can use them regardless of the project you're working on. For example, project management is one such skill. Another example is control theory. It's not just for embedded systems, but it happens to be very useful for specifically embedded systems. But let's have a look at an overview of the skills before we actually dive into each skill in sequence. The first skill that we're going to talk about is embedded systems design as a whole, and you need this skill in order to be able to build efficient and reliable systems through good systems architecture, and this is all about kind of creating this systems architecture. Number two is programming languages, so you need to be proficient in programming languages so that you can write efficient and maintainable code and optimize the system performance. Number three is microcontroller programming, so that you can understand how to use programmable hardware to achieve what you need to achieve in your application. Number four is real-time operating systems, so that you can ensure timely task execution and avoid inventing your own scheduling algorithms and things like that. Next skill is electronics and circuit design, so that you can design your own schematics and electronic circuits and not be dependent on existing hardware that is out there. Next skill is PCB design and layout, so that you can, lay out those schematics and actually produce a PCB. Next is FPGA development, and this is very useful if you want to enhance your design with custom hardware that you don't want to kind of create as discrete components, but instead you want to use a programmable logic chip so that you can just, create your digital hardware and upload it into this chip and then have really fast and really efficient digital hardware that you can use to extend your existing design. Next skill is signal processing, because everything is about signals and filtering those signals, gathering those signals, making sure that those signals are usable for control tasks. So signal processing is very important as well. Next skill is communication protocols, and you need to understand this so you can pick the right protocol for the job, depending on whether you're doing industrial automation or networking or on PCB communication, just between chips on the same PCB. So understanding those protocols helps you to be able to debug them. Next skill is control systems design, and this skill you need in order to build precision control into your application, so you don't have to guess parameters, but you can use mathematics to identify the right parameters. Next is sensors and actuators, and just being aware, of the vast amount of sensors and actuators that you have access to, so that you can pick the right ones for your application. Next skill is debugging and testing, which spans both the software realm and the hardware realm, because you need to both test your software and your hardware, and there's a lot of specific strategies and skills that are involved in this task of testing and verifying your designs. Next is software development methodologies, and this is all about Scrum and organizing source code, being able to maintain source code, and being able to work efficiently with large amounts of source code. Next skill is project management, and this is a little bit different from software development methodologies. This is about the whole project as a whole, with everything included there, like people that work on the project, the return on investment of the project, and all of those project management tasks. And next skill is cybersecurity, which you need to understand in order to build devices that are secure. And the last skill is machine learning and AI, because this is an area that is constantly expanding, and there's lots of new stuff happening in the AI space. So that is also a very important skill to have in your skill set of embedded systems development. So next we're going to look at each skill in sequence, and in each skill what I've included is a short description of each skill, additional skill areas that each skill can be broken down into, detailed resources that support each skill area, Some skill areas include direct links to open source projects. So you know, you can look at open source hardware to learn how it's made. Some skills are already covered by the training available at swedishembedded.com, and all skills are included in the Swedish Embedded Consulting offering. So let's get started and just dive into the skills then. The first skill we're going to look at is embedded systems design. And this is kind of like the overall system design task of the project. We can further subdivide this skill into 5 distinct areas, where the first area is requirements gathering, which is kind of driving the project, because it's always the requirements that decide what you're going to even do in the project. The second skill area is hardware selection, so picking the right hardware for the project, deciding on the components. The third area is software development, which is designing the software architecture, the software system. And the next area is system optimization, so that you can make the whole system more cost effective to produce. And the last area is scalability and modularity, so that you can reuse components that you create and reuse them in many different other products. There are some resources that I decided to include around this skill, and these resources basically show you examples of existing systems that have been designed that you can study. They are open source, they are open hardware, so you can get the schematic, get the hardware, study how it all works. And the first resource I want to mention is 99 Boards, which is a website that outlines several specifications of different types of boards. So they have industrial boards, they have system on module, and all of these boards are designed to kind of work together. So it's a very nice set of specifications that you can work with to create your own products and make sure that your products are compatible with other boards that are out there. Number 2 is Arduino, which is the most well-known platform. One thing to understand about Arduino is that it doesn't actually teach you good software design, but it's a good platform to get started with. So as soon as possible, once you get started with embedded systems, you should really move away from Arduino, but it's a good platform to get started with. The next board is the Raspberry Pi, which is probably the best system to get started if you're getting started with Linux boards. It's the simplest Linux board out there, so you can run Linux on it. You can experiment with building Linux images and running them on the Raspberry Pi, so it's a good starting system for Linux programming. The next project is the RepRap printer, which is the first self-replicating 3D printer. It has the hardware and software freely available, so you can study it, how it works and how it's designed. Then we have the OpenROV, which is an open source underwater vehicle platform that you can use for underwater vehicles. And there is software, electronics, hardware, everything available openly. Then we have the FarmBot. It's an automated farming robot, so kind of like a CNC machine, but basically specialized around farming. Then we have OpenMV. This is a machine vision platform designed around a camera and an STM32. Also, a lot of resources available, so you can study how it works. OpenCores is a library of processor cores. So you can look at how processors are made, how the code works, and you can use the existing cores to design your own processors. Open Compute project is centered around specifications of servers and network equipment. And then we have a global network of open source satellite ground stations, which is also a fascinating project that I wanted to include here. Mycroft is an open source home assistant platform, which is kind of looks like this, and it's a home assistant that is open source. Then we have the Marlin firmware, which is the firmware for 3D printers, which you can also study. Fascinating project. Open Brain Computer Interface is a project centered around creating brain-computer interface. So you have a bunch of sensors and lots of resources around this area. Then we have open source solar power, Libre Solar. a set of schematics and software for solar power, and an open source plastic recycling machine, which looks like this. So that's it for this skill. This is kind of like the overall design of the system, and now we're gonna go into more detail. Skill number 2 is programming languages. You have to, of course, be very proficient in programming languages if you're going to work with embedded systems. And the main programming languages is, of course, C, C++, a little bit of C++ because we don't usually use C++. Assembly language is good to know, not strictly necessary, but good to know. C# is very useful because it's used in Renode to create simulated hardware. Python is also very useful because a lot of CI processes are created using Python, and Rust is also rapidly becoming a very popular language in embedded development because it's such a well-designed language. And other languages are a bonus, of course. So if you know, the more programming languages you know, the easier it is to learn new programming languages for you. Programming core areas is so basically the skill of programming. We can subdivide it into 4 core areas, and number 1 is code optimization. It's basically creating efficient code to solve the problems you're trying to solve. Number 2 is hardware interaction, because in embedded systems we work a lot with hardware, so we need to configure and program the hardware. Number 3 is platform libraries. So once you understand a programming language, the next problem that you have is understanding all of the platform libraries and how to use them and kind of how to leverage them to solve your problems. Number 4 is debugging techniques, so that you can debug your code and find faults in it and create code that is kind of by nature easy to debug, because you don't want to have to dig through a lot of highly complex code when you're trying to find a bug. So debugging and testing is also very central to programming, to the skill of programming. There are a few resources I want to mention here. Number 1 is the GNU-C manual, and this is kind of like a very comprehensive manual of the C programming language. So if you want to understand all of the peculiarities of C, you can check out this manual. Number 2 is BG's Guide to C Programming, which is quite a long book, which is also about C programming, and it's very comprehensive. So check it out. The links are in the article. And number 3 is the Embedded Rust book, which deals with Rust for bare metal systems, basically. So there's a lot of peculiarities of bare metal systems, and this book kind of describes how to use Rust on bare metal systems. Skill number 3 is microcontroller programming. So once you understand the programming languages, the next thing you need to do is basically program the microcontrollers and to understand how to use the microcontrollers in the best possible way. So we can subdivide this skill into 5 different sub areas, which is number 1 is the architecture. So understanding your microcontroller architecture, what chip are you working with? Is it ARM? Is it x86? Is it Spark or something else? Number 2 is peripherals, so that you can program them efficiently and to interact with the physical world, because the on-chip peripherals is the primary way we have to interact from our software with the physical world. Number 3 is interrupts, and to be able to use interrupts efficiently so that you can design robust and responsive firmware. Number 4 is low-level programming, so that you can work with hardware features and not be limited by higher level language. So assembly might come into play here. And the last area is power management, so that you can create highly power efficient software on the particular microcontroller that you're using. So what are some of the resources here? And I've decided to include some books here, which are very good books. You can find them online if you just search for the book title and the author. So number one is digital signal processing using the ARM Cortex-M4, which is a book that is focused on ARM, but deals with the digital signal processing topics. So it's very useful if you're using ARM in your project and you want to understand how to accelerate signal processing on the ARM architecture. Number two is Definitive Guide to ARM Cortex-M3 and M4 processors by Joseph Huey. It's a very comprehensive book, specifically around Cortex-M3 and M4. And Joseph also has another, he basically has a series of different books. And another one that is also very good is System on Chip Design with ARM Cortex M processors. And this book deals more with kind of designing the system on chip, so the chip itself, but it's useful if you want to understand how the architecture is put together. So especially if you're going to be simulating those chips in Renode, for example, if you're setting up some tests, understanding how the architecture works kind of helps you with that, because it gives you more intuition around how the chip is put together. Then we have the AVR resources. AVR, I don't use AVR much at all in projects. I think it's a very simple architecture, and it's kind of it's kind of less efficient to work with AVR than with STM32, because we have just so much better tools when it comes to 32-bit controllers. But you can still study AVR. There's a few resources here. Then I've included some Texas Instruments resources around the MCP 430X family user guide. And you can basically look at different chips and look at their user guides and look at resources around the specific chips that you're working with. So for example, here is STM32. This is a book about STM32. And it kind of provides you with some tips on how to get started. Then we have how to get ADC accuracy. This is an application note from ST around ADC accuracy. So there's a lot of these application notes that you can have a look at to kind of understand how to use the microcontroller better. And then there is another application note around power modes. So that's it for the microcontrollers. So let's move to the next skill. Skill number 4 is real-time operating systems. And RTOS gives us 4 main benefits. It gives us managed execution so that we can rise above single loop architectures. It gives us multitasking so that we can have multiple independent code loops in one application. It gives us efficient resource sharing without having to make task switching explicit. And it gives us decreased complexity because RTOS makes things simpler if you know how to leverage it. There are 6 main knowledge areas into which we can split the skill of real-time operating systems. So number 1 is task scheduling. So it's the scheduler itself and how it works, how to make sure that it's predictable, and how to make sure that you get what you expect from it. Number 2 is inter-task communication. So once we have tasks running on our system, how do we actually communicate between those tasks? And this is where we cover semaphores, conditional variables, mutexes, and other types of inter-task synchronization and communication mechanisms. Number 3 is resource management, so that we can utilize RTOS to the fullest for managing resources and sharing them effectively between the different tasks. So we have this inherent hardware parallelism that is built into the hardware, but we cannot leverage it without an RTOS. So RTOS gives us this resource management where we can interact with different devices and switch between tasks when one device needs to wait for some I/O. Number 3 or number 4 is RTOS platforms. So you need to understand different platforms, what are the benefits of each one of them, and pick the right platform for your application. I personally prefer Zephyr RTOS because I think it's probably the best designed RTOS platform out there. Number 5 is configuration in CI. So when you start using an RTOS, the next thing you need to really worry about is configuring your CI properly. And I do deal with this in one of my courses where we look at CI setup for Zephyr specifically. But CI is really important because you want to make sure that your CI is set up in such a way that every merge request that your team is creating can be verified before it is merged. So you need to give special thought on CI, especially if you're using RTOS, because it's a more complex system than simply using code that you compile to run on bare metal. And the last area is RTOS debugging, which is basically involves those additional features of an RTOS like tracing, which you can enable in RTOS configuration, and you can get the data out of the system and then view it in, for example, system view. But those techniques are only available to you if you're using an RTOS. I've decided to include a few resources here. Number one is a Swedish Embedded Platform SDK, which is designed for CI infrastructure setup with Zephyr RTOS. And it kind of gives you this DevOps implementation for Zephyr RTOS. Number two is Real-Time Systems, Design Principles for Distributed Embedded Application by Herman Koppetz. It's a very good book that provides an overview of real-time system design principles and covers topics such as scheduling, algorithms, resource management, and all of those things. FreeRTOS is a very simple RTOS that is useful if you have a very small application that runs pretty much on bare metal, but you still want to have a basic scheduler for your application, so you can have efficient use of resources. So FreeRTOS is perfect for that. Zephyr RTOS is the proper RTOS for IoT devices that is very well designed and very state-of-the-art. Reynolds Simulator is a very powerful simulator for simulating your system so that you can set up verification constraints on your final application. You can kind of you can modify the hardware in simulation, and then you can verify that your firmware responds appropriately. Notex is another small RTOS that provides a POSIX-like interface. It's actually something that it says that it does probably the best, providing a POSIX-like interface. Then there is a few other RTOS projects. There is Chibi OS, which is a small footprint, low overhead RTOS. There is Riot, which is designed for IoT devices and low power wireless. And then there is Fuchsia. This project is actually a project that I've never heard of before until very recently, but it's actually an RTOS developed by Google that they don't really advertise much, but it's an RTOS that they use for their Google Home devices. All right, so then let's go to the next skill. Skill number 5 is all about electronics and circuit design, and you aren't truly free in your embedded development unless you learn circuit design, because existing boards are usually limiting in what you can do with them. But if you learn circuit design, you can design your own boards. We can subdivide circuit design into 6 different subtopics. Number 1 is analog and digital electronics, so that you can design analog circuits and you can design digital circuits. Number 2 is circuit analysis, so you can analyze and verify your circuits, for example, in LT-SPICE, to know that they are gonna to understand how they're gonna behave before you actually even build the prototype. Number 3 is a component selection, which is very often driven by manufacturer specifications and manufacturer suggestions that you get from datasheets and application notes. Number 4 is power supply design, and this is a very important part because power supply is one of the most important components on your board. If you get your power supply wrong, you can easily fry components on your board, and you can get failures that are very unpredictable. So understanding how to design power supplies is a very important subtopic of circuit design. Number 5 is signal integrity, to be able to maintain signal quality in your design, and to be able to anticipate potential problems with signal quality. And number 6, prototyping and testing. You should be able to create your own prototypes, solder your own boards, debug them, resolder some components. That's a very useful skill because it really lets you fix problems very quickly. So you can just take out your soldering station and resolder a component, and that just saves a lot of time. Some of the most useful resources in circuit design, there's a few books that I would like to mention. Number one is Electronic Circuits by Adel Sendra. This book provides introduction to both analog and digital electronics, covering topics such as semiconductor devices, amplifiers, filters, and digital circuits. Number two is Electronic Devices and Circuit Theory by Robert Boystad. This book covers the fundamentals of electronic devices and circuits, with emphasis on analog circuits, including topics like diodes, transistors, operational amplifiers. And even if you're working predominantly with digital circuits, you're still gonna need to design analog circuits sometimes, because a lot of sensors emit analog signals, and you're gonna need to condition those signals. You're gonna need to convert between voltages, and that's where analog circuitry comes into play when it comes to interfacing those sensors with your digital microcontroller. Number three is Digital Design by Maurice Mono. This is a very big book, and it focuses on electronics and provides a thorough introduction to digital circuit design, including combinatorial and sequential logic, as well as design using hardware description languages such as Verilog. Another very good book is Analog Integrated Circuit Design by Tony-chan Karusone. And this book covers the design and analysis of analog integrated circuits with an emphasis on CMOS technology. And it includes topics such as operational amplifiers, comparators, and data converters. Another book is Engineering Circuit Analysis, which provides comprehensive introduction to circuit analysis. And the third one is Basic Engineering Circuit Analysis, which covers fundamentals of circuit analysis, including the basics like Ohm's law and Kirchhoff's law, but also circuits theorems, AC and DC circuit analysis techniques. Another very good book is The Art of Electronics, which is very comprehensive and provides an introduction to electronics, including in-depth discussions on various components, their properties, and how to select them for specific applications. So this is a lot about component selection. Then we have a book called Electronics for Embedded Systems. This book focuses on electronics for embedded systems and covers components, their properties, and how to select them based on system requirements. And then we have High-Speed Digital Design, which is a handbook on really high-speed design. And it provides a comprehensive overview of the high-speed design principles with an emphasis on signal integrity issues. And another good book on signal integrity is Signal and Power Integrity Simplified by Eric Bogatin. And this book covers both signal and power integrity in electronic systems, with focus on high-speed and mixed signal designs. And of course, last but not least, I would like to include Louis Rosman's channel, because it's a very good channel on soldering techniques and prototyping. Even though his channel is about MacBook repair, it teaches you a lot about soldering techniques and really working with prototype boards. Let's see if this page even loads. Basically, this link points to a long playlist where you can watch him basically repair MacBooks, but you get so much insight on how you can solder better, even when you're working with your own custom circuits. And it's a very nice thing to have in the background, kind of listening to all the problems that occur with MacBooks. So that's it for this skill, and let's go to the next one. Skill number 6 is PCB layout. So once you have your circuit designed, now you need to lay out the circuit so that you can manufacture the board. And we can subdivide this skill into 6 different areas. Number 1 is master and design tools, so that you can design circuits and lay out the boards effectively. And design tools include Altium Designer, KiCad, Eagle, OrCAD. Next is component placement, so that even if you're using automatic routing, placement is extremely important, because placement will determine how the automatic router is going to route your board. But most of the time, it's actually more efficient to do manual routing, but placement is very important because it sets up your whole layout of the board. You need to anticipate things like being able to route several signals through the available space. You need to think about interference. You need to think about the size of the components. So component placement is a separate area. Then we have routing, where we actually lay out the copper tracks on the board, and that has a lot of its own peculiarities, like impedance matching, distance between tracks, thickness of the tracks. There's a lot of work that goes into that. Then we have multi-layer design, where you have multiple layers and you can have hidden bias, and you need to change layers appropriately. You need to understand what implications it has for your signal integrity when you change layers. You need to place proper ground planes beneath your signals so that you get good signal integrity. So multi-layer design is, it gets more complicated the more layers you have. Most of the time you're going to use 4 layers. 4-layer boards are fairly standard, but if you have very complex PCBs, you might go for 6 or 8 layers or more. Next, we have design for manufacture. So it's important that the board is manufacturable. So, for example, if you have very sharp corners in your tracks, then you might get artifacts on the PCB. It might not be manufactured properly because there is this liquid that gets trapped between the tracks, so that the track may actually be thinner than you design it to be. So there's a lot of little details that you need to pay attention to when you design for manufacture. And the last topic is design for testing, so that you make sure that you place enough test points, that debug ports are easily accessible, and things like that. So really considering the fact that you are going to have to test your board, and you need to design for testing from the very beginning. Some resources. So first of all, I want to mention the different CAD packages that are available for PCB design. First of all, we have Altium Designer, which is very powerful PCB design software and offers a comprehensive suite of tools, including schematic capture, layout design, and signal integrity analysis. Altium is probably the most comprehensive tool for circuit design. Then we have Autodesk Eagle, which is very user-friendly, a good software to start with. I actually started with Eagle. That was my first PCB design tool that I used. Then I briefly used Altium, and finally I settled for KiCad for anything that is below 100 components. Because KiCad is open and you have full access to the file format, so you can run checks using Python, so it's very convenient in that sense. And then there is Cadence OrCAD, which has been used for many years. Then we have some resources specifically on PCB layout, and I want to start with a book called Right the First Time, The Practical Handbook of High-Speed PCB and System Design. This covers various aspects of high-speed PCB design. It focuses on high-speed design, including signal integrity, power distribution strategies, and specifically from the perspective of high-speed design. Then we have printed circuit board design techniques for EMC compliance, how to design boards that would pass EMC compliance. Then we have RF circuit design, which is focused on radio frequency signals, so laying out the PCB so that it doesn't emit too much interference, so that the signals are maintain their integrity and things like that. Then we have a few interesting companies that provide PCBs and sources for their PCBs. So first of all, we have Olimex. This company provides open hardware designs for a lot of different boards. So pretty much all of their boards are open hardware. So you can go here, you can download, you can go to GitHub repository and download the hardware design. And all of their boards are open, so you can get designs for all of these boards. Then we have Open EVSE, which is an open source electric vehicle charging station, which also provides hardware designs. And then we have a very nice blog post by Jay Carlson that deals with design of Linux boards. So this is primarily targeted at Linux boards, and he talks a lot about different Linux boards that you can build. And he actually provides you with a lot of examples here on routing, design, and everything else, signal integrity. And he covers designs using several different microprocessors. So this is a very good read, very interesting. The link is in the article. Okay, that's it for PCB layout. Let's go to the next skill. Skill number 7 is FPGA development. And this has several benefits. It gives us programmable digital logic so that we can build highly precise time-critical extensions to our designs. It gives us ability to do CPU prototyping so that we can evaluate CPU designs very easily by just loading them into this programmable logic chip. And it gives us ability to capture and process signals that may be very time sensitive, and we have to be very fast when we capture them and process them. So FPGAs are perfect for that. We can subdivide FPGAs into 6 different knowledge areas, where the first one is understanding the FPGA architecture. So FPGA is basically a chip that comes with memory cells and logic that you can program. So you can basically create different gates from these available logic blocks in the FPGA, and then you can compile Verilog into a binary image that contains configurations for all of these gates, and then you can interconnect them together. So FPGA has a lot of internal components in it that can be used in many different ways. And if you're going to optimize the design, you need to understand how those blocks work and what they're used for. Then we have hardware description languages, so knowing Verilog or VHDL and being able to write the code in those languages, which you then compile into this FPGA binary image. FPGA design tools like Xilinx tools, for example. Optimization techniques. This is a lot about logic and kind of understanding how can you optimize your design so that you minimize the number of gates that you're using, trying to fit the design into an FPGA with limited resources. Then we have IP cores and soft processors, and this is a whole area of knowledge that is specifically just focused on processors. And if you've seen the link that I provided before to the Open Course website, it provides a lot of different cores with source code that you can have a look at and learn. And you can then design your own cores and load them into the FPGA and then run firmware directly on those custom cores. And then knowing the different FPGA development boards, basically being familiar with the development boards that are available and how you can use them to prototype your design. So some of the most interesting FPGA resources, I decided to include some projects that use FPGA, and one of the most interesting projects is the homemade FMCV 6 GHz radar, where this device is based on an FPGA that captures the radar signal and kind of gives you ability to read out the signal over USB. And it contains all of the source code. You can inspect how it works, and there's a lot of explanation on the website that shows you basically what the results are. Then we have open source FPGA stereo vision core that is focused on stereo vision and basically calculating the depth map and a few other things. And we have also a resource about radar perception, which contains a lot of links to other resources. So this repository has a lot of links to different projects and SDKs and papers and other things. It's very interesting. Then we have software-defined radios, of course, and that's probably the most well-known use of FPGAs, where you use the FPGA to create software-defined radios. And I linked to this repository. This is from ZipCPU. ZipCPU also provides a lot of different CPU and peripheral designs, which are also open source. Then we have Lime SDR, which also uses the Altera FPGA as the main chip to implement a software-defined radio. And then there is a book called FPGA Prototyping by VHDL Examples. This book contains a lot of VHDL examples for different types of peripherals that you can have on an FPGA. So FPGAs are a good way to extend your design with high-speed digital circuitry, basically. All right, let's go to the next skill. Skill number 8 is signal processing. And signal processing is critical for embedded systems because everything we do is basically signals. We have two different types of mathematics. We have continuous time mathematics and discrete time mathematics, which are slightly different, but basically describe the signal in continuous and discrete time. And we have to deal with a lot of noise because noise is everywhere. We need to condition our signals, filter them, and for that we use signal processing. We can subdivide signal processing into 5 different areas, so different knowledge areas. Number 1 is time domain analysis, which works with signals in the time domain, basically a series of measurements, and they're measured in time. Number 2 is frequency domain analysis, and this is dealing with signals that are periodic and expressed in frequency domain. So you can do a lot in frequency domain, which you cannot do in time domain. But you can do, for example, system identification in time domain, and you can do system analysis in frequency domain. You can measure your response of your system and plot it as a Bode plot. Then we have digital filtering, which is a major area where we design filters using mathematics, which is very useful for embedded systems. And then we have analog filtering, which is what we do outside of our software, but still on the PCB. So we might need to do some analog filtering before we sample the signal, and then we do digital filtering in our firmware. But both use similar equations to design those filters, and all of this is part of signal processing. And then we have, finally, adaptive signal processing, which is signal processing where we can adjust parameters depending on circumstances. So we can adjust, this basically deals with how do we adjust filter parameters depending on different disturbances. Some of the best resources on signal processing is a book called Signals and Systems by Oppenheim. And this is a widely used textbook covering fundamental concepts of signal processing, including time domain analysis, signal properties, and basic operations on signals. Then we have design and operational amplifiers, design with operational amplifiers and analog integrated circuits. This focuses on amplifiers. Then we have adaptive filter theory, which deals with adaptive signal processing. There's a very good resource on Kalman and Bayesian filters in Python, which is kind of like a book, but it's very comprehensive with a lot of examples, and there is even Python code that you can execute directly online to better understand how Kalman filters work and how to work with them in Python. Very comprehensive resource, a lot of examples, a lot of theory, so definitely check it out. Then we have the Control System Toolbox, which is available as a GitHub repository under Swedish Embedded /control. This provides a lot of building blocks for building filters and building control algorithms. Then we have the Scientist and Engineer's Guide to Signal Processing by Stephen Smith, and this is actually an online resource, basically DSP book. It's also referred to as DSP book. And this provides a lot of theory and a lot of explanations around signal processing. So this is an online resource which you can check out directly by just clicking the link in the article. Skill number 9 is communication protocols. So we have the signal processing, we have the signals coming in and out, but then on top of these signals, we have communication protocols. And you need to understand communication protocols because depending on what devices communicate between each other, you're going to use different protocols, and you need to understand what's available to you. We can subdivide communication protocols into 6 different areas. Number 1, we have serial communication protocols. These are often used directly on the PCB, so it's UART, SPI, I2C. Of course, UART you can use between different boards, but you would typically have a transceiver that converts voltage levels. So maybe you would use RS-232 instead of UART, but it's kind of the same protocol, but it's different voltage levels. But you need to understand how these work. Then we have network communication protocols. These are used for communication over general purpose network infrastructure. And these include TCP, UDP, EtherCAT. Then we have industrial communication protocols. These are CAN bus, Modbus, and Profibus. These are used for robust communication between devices in an industrial environment. Then we have the wireless communication protocols, which include NB-IoT, Zigbee, LoRaWAN, Bluetooth, Sigfox. These have their own peculiarities. So if you're going to build IoT systems, you need to understand wireless communication protocols. And then on top of all of these protocols, we have additional IoT communication protocols. So on top of wireless, we could transmit MQTT frames or COP frames, which would actually be Ethernet frames, which will then be passed over a UART, for example, or over a wireless link. So a lot of these higher level protocols build on the lower level protocols, and you need to understand how do you split the packets into transmissible units that you can then send over a lower level protocol. For example, with UART, you would be dealing with framing. You need to have framing if you're going to have reliable transmission of a higher level protocol. And then we have communication security, of course, and this deals with encryption of the communications to make sure that all of the communications that are done over these protocols are secure. Some of the resources, number 1 is the Wireshark network analyzer, which also works for analyzing USB traffic, for example. There is a lot of plugins that you can have that allow you to analyze Bluetooth traffic as well. You can connect Wireshark to simulations and analyze traffic that is coming out of simulation. So it's a very useful tool. Then we have the logic analyzers, which you can connect directly to your PCB. And this is where design for testing comes into play, because you need to have designed your board appropriately so you can connect the logic analyzer to it. But then you can use these tools to decode protocols, to inspect digital signals, and basically debug your board. Then we have some more simple resources on the basic communication protocols. There's a lot of information from Analog Devices that explain how these protocols work. We have UART, we have SPI, we have I2C. Most of the complexity of I2C is the state machine. So if you're coding an I2C driver, you would be dealing a lot with this different state transitions of the I2C protocol. And then we have the CAN protocol primer that gives you more information about the CAN protocol. Skill number 10 is control systems design. So whenever you're building an embedded system, most probably it's going to either be a communication system or a control system. So communication systems basically involve sensors that connect over some wireless protocol and then transmit data, while control systems read sensors and control actuators. And control systems design is the big area that encompasses all of the mathematics that go into controlling dynamic systems. So we can further split control systems design into 6 different areas. We have linear control theory, which deals with linear systems that can be expressed as a number of linearly dependent variables or parameters. We have nonlinear control theory, which deals with variables that have nonlinear relationships. We have robust adaptive control, which deals with adjustments of parameters to deal with uncertainty and disturbances. And then we have optimal control, which deals with optimizing the control parameters based on a cost function. Then we have model predictive control, which uses a model that is run in parallel to the real system which gives the controller an ability to predict how the real system is going to behave, and then calculate the control action based on the output of this simulated system. And then we have network control systems, which basically deals with behaviors like swarming, mesh networks, and different types of systems where you have many agents that work together. Some of the best resources on control theory is Feedback Systems, an introduction for scientists and engineers by Astrom. This is one of the best resources and best books probably out there on control theory. Then we have Modern Control Engineering by Ogata. It's an excellent book that covers control engineering topics, including state space analysis, linear system theory, and control system design using modern techniques. Then we have Control System Design by Goodwin, which is a comprehensive introduction to control systems and deals mostly with single input, single output, and multiple input, multiple output systems. And then, of course, we have the Control Systems Toolbox, which provides you with C library functions for control system design. Skill number 11, sensors and actuators. This is a major one. This is actually a very long section in this article and in this video, but I'm not gonna go over every single one of the sensors here. I'm just gonna kind of cover the broader categories of sensors and then present you with the different types of sensors on the screen. So we have basic sensors, which is buttons and joysticks. We have temperature sensors, which can have 4 different types of implementations of these sensors. You can have thermocouples, resistive temperature detectors, thermistors, and infrared thermometers. Then we have pressure sensors to measure pressure. We can have piezoresistive pressure sensors, capacitive pressure sensors, optical pressure sensors, and resonant pressure sensors. Then we have flow sensors, which measure flow of something inside something. So we can have mass flow sensors, we can have volumetric flow sensors, ultrasonic flow sensors. These are very useful, for example, for measuring water flow, electromagnetic flow sensors, and optical flow sensors. Then we have level and distance sensors. We can have capacitive level sensors, ultrasonic level sensors, optical level sensors, optical time of flight sensors, float level sensors. We can have position and displacement sensors, which can be linear variable differential transformers. We can have potentiometers, we can have encoders, we can have inclinometers. And another one actually that I would like to include here is laser-based position sensors. So they basically use a camera that can read a barcode, for example, and then it can determine exactly where this barcode reader is along a barcode line. There's actually sensors that work like that, but they're not very common. Then we have force and torque sensors. We have strain gauges, we have load cells, we have piezoelectric force sensors, we have torque transducers, we have acceleration and angular velocity sensors, very common in applications like drones, for example. We have accelerometers, we have gyroscopes, we have seismometers. Then we have humidity sensors. We can have capacitive humidity sensors, we can have resistive humidity sensors, and depending on like what your application, what requirements you have for your application, you would use a different type of implementation of a sensor. We can have a thermal conductivity humidity sensors, we can have optical humidity sensors. And then we have gas and chemical sensors, which also come in different categories. We can have electromechanical gas sensors, infrared gas sensors, photoionization detectors, metal oxide semiconductor gas sensors. Then we can have light and radiation sensors. We can have photodiodes, we can have phototransistors, we can have photoresistors, we can have Geiger tubes that count how many hits it gets from a radioactive source. We can have proximity sensors, and these can be inductive-based proximity sensors, capacitive proximity sensors. So, for example, like buttons would be a capacitive proximity sensor. Ultrasonic proximity sensors send out a wave and get back a result. Infrared proximity sensors. Then we have imaging sensors, which basically deals with cameras, but also LiDAR is an imaging sensor. We can have cameras like CCD and CMOS sensors. We can have color sensors that just detect the color. We can have LiDAR that scans around it and basically measures distance. And we can have an optical fiber sensors that measure different properties of a signal inside an optical fiber. Then we have acoustic sensors, basically microphones, hydrophones, ultrasonic sensors, and acoustic emission sensors. So for example, a normal microphone doesn't detect ultrasonic sounds. You need to have a special ultrasonic microphone to receive ultrasonic signals. Then we have magnetic sensors. We have Hall effect sensors used a lot in motors. We have magnetoresistive sensors, flux gate magnetometers, magnetoresistive sensors. And then we have electrical sensors, voltage sensors, current sensors, resistance sensors, capacitance sensors. And then we get into actuators. So the most basic actuator is a LED, basically just flash a light. Then we have DC motors as actuators, very common in different types of servos, different types of industrial automation. Then we have AC motors, which give more power, a little bit more complex to control, but more effective, more efficient in terms of energy consumption. We have stepper motors that give you ability to move the motor in distinct steps. Then we have servo motors that take in a signal and basically position the servo exactly at the required position. We have linear motors that move in a linear fashion. We have solenoids that move a core back and forth, or for example, a relay is also a solenoid. We have piezoelectric actuators, which are ceramic actuators which can move very small distances. We can have shape memory alloy actuators. We can have voice coil actuators, basically like speaker, but more like a generic type of voice coil. We can have magnetic levitation actuators, where you have a magnet, electrical magnet, and then it kind of levitates another magnet, and then you can have motion in that way. We can have hydraulic actuators. We can have pneumatic actuators. So there's a lot of different sensors and actuators that kind of all give you this array of possibilities to choose from when you're building your embedded system. So you need to understand what you have available so you can pick the right sensors for your embedded application. Skill number 12 is about testing and debugging. So testing and debugging is a crucial review tool, especially testing, because you can look at tests and that can give you an intended behavior of a code, and that makes it very easy to review code without actually having to run it. It automates quality assurance because you can run tests in CI and automate those test scenarios. And it enables you to fix bugs early because it's always cheaper to fix a bug early than to wait and fix it later. We can subdivide testing and debugging into several knowledge areas. Number one is different debugging techniques, basically stepping through the code, inspecting variables, inspecting the stack, inspecting specific registers that contain, for example, the return address from an interrupt. So understanding what techniques you have available for actual debugging. Also simulation debugging. You can have your firmware running in a simulator and then connect to it using GDB and then do conventional debugging, but in a simulator instead of the real board. Then we have unit testing. Is also an area that focuses on specifically on logic verification. So unit testing is a lot about checking every path through the code and checking the logic that occurs during that, like over that path in code. So you can set constraints on, for example, parameters passed to functions that are outside of your unit being tested. You can insert return values for this outside function. So unit testing deals a lot with kind of testing the internal logic at the lowest level of each function in your code. Then we have integration testing, which checks the higher level APIs and how components can integrate together and integrate with hardware. And then finally, we have system testing, which deals with simulation of the production firmware and running scenarios against the simulated firmware. So this here we look at, for example, Reynolds testing and robot framework and simulation drivers that simulate different types of hardware and things like that. Then we have validation and verification, and this is more about sort of modeling your software and validating it at the logical level. So you can have, for example, formal verification. You can rewrite your algorithm into logical language that can then be verified using a formal prover. And then we have test automation that deals with the automation tasks of running tests in CI and collecting the results of the test, for example, generating coverage and presenting a coverage report and things like that. Some resources that I would like to mention is a course called CI DevOps Infrastructure for Embedded Development. In this course, I basically go over how to set up CI infrastructure for a Zephyr-based project. Then we have a really good book called Test-Driven Development for Embedded C by Grenning. This explores test-driven development and gives a lot of very high-quality advice on test-driven development, specifically for embedded C programming. Then we have Embedded Software, The Works, which is quite a comprehensive book that covers many aspects of embedded software development, including design, coding, debugging, and testing it. So that's it. Let's go to the next skill. Skill number 13, software development methodologies. Software development methodologies, they deal with primarily working with large numbers of text files and managing them in an efficient way. So this is slightly different from project management, which we'll look at next, because software development methodologies are about working a lot with Git and working a lot in this incremental fashion. So continuous delivery, trunk-based development, all of these are software development methodologies. So software development methodologies deals with optimizing how well the team works with the source code that they're tasked with writing. We can subdivide software development methodologies into 5 different areas. So first of all, we have Agile and Scrum fundamentals. So to understand how you can split work into epics, stories, tasks, and subtasks. Then we have roles and responsibilities. And if you're applying Scrum, here you would have, for example, Scrum Master or Project Owner, and you need to understand the responsibilities of each team member so that you know what the rest of the team is doing. Planning and estimation, so being able to make good estimates of how long something is going to take. Then we have iterative development and sprints, so compartmentalizing work into sprints and completing them, making sure that every task is fully completed before it's actually marked as completed. And then we have continuous integration and quality assurance. Continuous integration is extremely important because it gives us ability to build software in small increments where every increment essentially results in a working product. So software development methodologies deal with a lot of those things and basically help us implement continuous delivery. I have a specific embedded DevOps training that deals with those software development methodologies and explains the importance of different concepts like trunk-based development, continuous integration, deployment automation, continuous testing, continuous delivery. Then we have firmware DevOps infrastructure, which I mentioned before, which deals with implementations of these ideas, specifically for Zephyr. And then we have a really good book called Agile Estimating and Planning by Con, which provides practical guidance basically on estimation techniques for Agile development. Another book is User Stories Applied, which deals with basically creating user stories for Agile development, mapping them out, and making sure that you can then split them into tasks and estimate how long something is going to take. Then we have The Art of Agile Development by James Shore. And this book is a comprehensive guide to Agile development, basically. Then we have Agile Coaching, which is a book about coaching in the Agile concepts. So basically coaching the team in understanding Agile concepts, but it also explains a lot about Agile concepts and also kind of helps you to communicate the importance of Agile concepts to the rest of your team. And then there is a really good paper called Personal Software Process, which deals with the personal process of software development. So how does every developer ensure that they can work effectively? Because the idea is basically that if every developer works effectively, then the sum total of the team is going to be effective output. So this paper deals with personal process of software development for every developer, which can be kind of applied to every developer. Skill number 14 is project management. Now, project management is kind of a higher level skill, which involves everything, not just software development methodology. And it doesn't replace Scrum. Project management is about the broader context. It is all about return on investment. How do we make sure that our projects are effective in generating results? And it is driven by stakeholders, where we are basically creating a project. The sole purpose of a project is to provide some kind of value to the customer or other stakeholders that are interested in the project. We can subdivide project management into 6 different areas. So we have requirements management. How do we collect requirements? How do we manage them and keep them up to date? Estimation and planning. How do we estimate how many resources we need to complete the project? Risk management, so that we can avoid surprises. Quality assurance and testing, so that we can make sure that all of the requirements are met. Infrastructure and CI. How do we make sure that we have proper infrastructure, not just for software development, but also for other things like collecting the knowledge of the team somewhere and making sure that new team members can access that knowledge. And of course, team management and leadership and communication, so that we can build effective teams. So project management is a lot about like building an effective team as a whole. There are some really good books on project management, where the first book is Project Management Body of Knowledge, which outlines all the different areas of project management. Then we have The Art of Doing Twice the Work in Half the Time by Sutherland. Very effective work on how to be more effective in projects. Then we have Ruthless Management of People and Profits by Dan Kennedy. This is a very good book on management techniques and on managing projects in general, or managing a business in general. Then we have Effective Executive, the definitive guide to getting the right things done. And then we have The Phoenix Project by Gene Kim, which is a novel that follows an IT manager tasked with rescuing a failing project and then provides insights into effective project management and good DevOps approach to project management. So DevOps is also a big area of project management, which kind of overlaps also with software development methodology. Skill number 15 is cybersecurity. So no matter what system we build, there is going to be a requirement for making sure that the system is secure. And cybersecurity deals with 4 main areas, which is cryptography. How do we make sure that our devices communicate with encrypted data streams? Number 2 is secure boot and firmware updates. How do we make sure that the device can verify the firmware that is being uploaded to it? How do we implement secure over-the-air updates? Then we have authentication and access control, so that we can control who is allowed to access different systems and when. And finally, we have network security, which deals with the rest of the infrastructure and how do we make sure that it's completely secure. So even if we are working with embedded systems, there can be other parts of infrastructure, for example, like MQTT brokers that the embedded system is communicating with. And those things need to be secure as well. Some of the resources that are worth looking into is Secure Coding in C and C++ by Robert Secord. This focuses on C and C++ programming and deals with potential vulnerabilities that you can avoid when you're coding specifically in C and C++. Then we have Security Engineering, a guide to building dependable distributed systems by Ross Anderson, which covers a wide range of security topics, including cryptography, authentication, access control. And then we have the Lavarand Cloudflare random number generator. So basically, Cloudflare is a service that maintains a lot of servers, and all of their servers need some kind of random number source that will guarantee that the numbers they use for encryption are completely random. So they've created this solution of having a bunch of lava lamps that generate different colors, and then they use those colors to create a random number. So you have red, green, and blue, and as a whole, this provides a random number. So They use this as an addition to conventional random number generation to make sure that their numbers are truly random. And finally, we have skill number 16, machine learning. Machine learning is coming out everywhere, and it's good to understand that machine learning is actually a generalization stemming first and foremost from control theory, where control theory deals with system identification and control algorithms, and then we have created this whole new area of machine learning where we can do broad system identification on systems with billions of parameters. So we can subdivide machine learning into 6 different areas. Number 1 is adaptive control, where we can adjust conventional controller parameters based on complex external circumstances and use machine learning to come up with the optimal parameters. We can, next is fault detection and diagnosis, so that we can identify impeding faults based on analysis of measured data. And this, just by looking at the data, it's hard to identify that there is an impeding fault, but machine learning can actually provide us with more insight into what potential faults are actually waiting to happen. Then we have model predictive control, where you can have a machine learning model imitating a very complex system, and then you can have a controller that uses that as part of the model predictive control algorithm. System optimization. Machine learning is very good at optimizing, and especially the newer types of deep learning can provide new ways of optimizing systems. So we can optimize not just parameters of a controller, but we can optimize systems, even more complex systems. Human-machine interaction, where we can augment some of the human functionality using machine learning, for example, like self-driving cars, where a car can follow a lane and just need minimal input from the human, and the human basically just needs to be there to make sure that the car doesn't do anything stupid. And last but not least, organizing knowledge. So machine learning has been very good at this, especially very lately, in organizing large amounts of knowledge. So we have whole new ways coming up that would allow us to access the collective knowledge of humanity and basically mine it for new insights. So there's a lot to be done here in this area in particular. Some of the best resources on machine learning specifically for embedded is number 1, Pattern Recognition and Machine Learning by Bishop. And this book covers machine learning, machine unsupervised learning, neural networks, and probabilistic graphical models for pattern identification. Then we have TinyML, which is machine learning using TensorFlow Lite on Arduino. And if you are not aware of it yet, Zephyr RTOS actually supports TensorFlow Lite, so you can run machine learning models on your embedded systems very easily. You can train them offline, basically on a computer, and then you can upload the model and run it in an embedded system using TensorFlow Lite to execute the model on the embedded system. And then we have the resource called Deep Learning, which outlines some of the basics of deep learning. It comes with different chapters of this book, which is accessible online. So that's basically it. 16 skills that constitute embedded system development. Most important, I would say, is programming, control theory, circuit design, and PCB layout. But all of the skills are important, and even software development methodologies are very important, because you would be more effective even if you're just working on a single project. You would be much more effective if you're using proper DevOps and CI setup. So look through the skills, find out more information. You can search online for different topics that I provided in this video. And it's kind of serves to give you an overview of what goes into embedded systems development, so that you can use it as a starting point, as a springboard to learn more about embedded systems. If you have any questions regarding this video, then comment on the video or comment on the article or the social post where you have found this video. and I would be happy to hear your thoughts, your questions, and any additional information that you can provide in addition to what I just covered here. If you think this content was good, then you can check out my books and courses and consulting. Basically, I have two main books right now out, which is number one is Modern Embedded Firmware Infrastructure, which deals with CI and DevOps setup, specifically focusing on Zephyr RTOS, CMOC, Unity, and Renode. And the second book is Embedded C Programming Design Patterns, which deals with design patterns for C programming, which shows you how to organize your C code and how to write clean code for embedded systems in C. Both of these books are also available as courses. So we have Ultimate Embedded Firmware DevOps Infrastructure, which is available as a Udemy course. We have Embedded C Programming Design Patterns, also available as a course. And we also have subscription, where you also get weekly Q&A calls on Wednesdays, where you can join and ask questions. So this is more of a personal guidance, where you can ask questions, get help with your existing projects, and it's available as a subscription model here at swedensembedded.com/portal sign up. So if you go to this link, you will basically get the different pricing models. So there's number one is free, which gives you access to the embedded insights. Number two is a student account, which gives you access to all of the recorded content. And the professional is the one that includes weekly Q&A as well. All right, if you think that this was good content, share it with your friends, and I'll see you later.